Section 6. Today's lesson is going to take a little bit of a jump away from solving systems of equations to now graphing linear inequalities. All right, now when we graph a linear inequality, there's actually going to be multiple solutions. A solution is simply one of the ordered pairs, xy coordinate, that will make the inequality statement true. And really our key concepts deal with graphing a linear inequality. So when we graph a linear inequality, we're going to have a line that we're going to start off by graphing, and this is going to be known as the boundary line. All right, so for example, over here in our xy plane, let's just say we have our boundary line, and then the inequality will mean that there are going to be many solutions, and that solution set then will be shaded. So for example, let's say we want all of the solutions, all of the ordered pairs that are less than or equal to that boundary line. So then we would shade all of those ordered pairs that are less than or equal to that boundary line. So this right here, this little ordered pair x, y would be considered a solution to that system. Sorry, not to that system, but to that inequality. In other words, it would make that inequality a true statement. All right, so that's how we're going to start off our examples today. We're going to determine if an ordered pair is a solution to the inequality. In other words, it will make it a true statement. So let's test the ordered pair -1, 9 on the inequality 2x plus y is less than -3. So we'll take our -1 and substitute that for x, and our +9 substitute that for y, and ask ourselves, does this make a true statement? So this is -2 plus 9, which is +7. Is +7 less than -3? Nope, this is false. So we would say that -1, 9 is not a solution to our inequality. All right, let's try example 1b. Now we're going to test the point 2, -2 for our inequality x minus 3y is greater than or equal to 8. So substituting 2 in for x and -2 in for y, we're going to test and see if that is greater than or equal to 8. All right, now make sure you follow your order of operations. This is -3 times a -2. So this becomes 2 plus 6. And in fact, 8 is greater than or equal to 8. It's equal to it. So this is a true statement. And we would say yes, that 2, -2 is a solution to our inequality. All right, now we're going to get into graphing inequalities on the coordinate plane. So this is very similar to graphing linear equations. However, when they're inequalities, remember, you're going to have to shade a particular region known as the half plane that contains all the solutions. So let's show you what we mean here. We're going to graph x is greater than 4. So first of all, we're going to start off by graphing the boundary line x equals 4. Now that would be this vertical line here that goes all the way through 4 on the x-axis. Now the one thing that's wrong with this solid line is that I don't want all of the x's greater than or equal to 4. I actually just want all the x's greater than 4. So I need to create what's known as this dotted line, this dotted vertical line. And that dotted vertical line means that the boundary line is not included as the solutions. All right, now I want all the x's greater than 4. So any point over here to the right is going to have an ordered pair where x is greater than 4. So I need to do my shading on this region to the right of my vertical line. Let's see if I can get that right up to that boundary line there. And there you go. I would shade this half plane, and I'd say, and this half plane here are my solutions to this inequality. Next, we're going to graph the inequality all y's less than -3. And you're starting to see that when you have just the greater than or the less than symbol, you're going to use a dotted line. So I want all the y's less than -3. So we're going to put our horizontal dotted line that goes right through -3 on the y-axis. Now, since I want all the y's that are less than -3, any ordered pair down here below that dotted line is going to have a y coordinate that's less than -3. So my solutions, or my half plane here, that would contain all those solutions, would be this entire plane shaded below my boundary line. All right, so that's a horizontal and a vertical example. Let's take a look at an example that's not horizontal and vertical, and also one that's going to have a solid boundary line. So now I want to graph all my y's that are greater than or equal to 2x minus 3. So we're going to start off by graphing this boundary line. It's got a slope of 2 and it's got a y-intercept of negative 3. So we'll plot negative 3, and then we're going to rise 2 and run 1. And we will graph our line, and now since it's greater than or equal to, I can actually connect these with a solid line. So let's get that nice and solid and straight, and that's not even close, so we're going to erase that and try it again. All right, there's our solid line that goes through those points as best we can. Now, how do I know which side to shade? Do I shade the y's that are above this, or do I shade the y's that are below this line? So the best thing to do is to test the point 0, 0. Let's test 0, 0 to see if it makes a true statement. If 0, 0 makes a true statement, then we know to shade the region in which 0, 0 lies. So let's put 0 in for y. Is that greater than or equal to 2 times 0 minus 3? Well, that gives me the statement 0 is greater than or equal to negative 3. And that's actually a true statement. 0 is greater than a negative number. So I know 0, 0 lies in the solutions. So I am going to shade the part of my graph in which 0, 0 lies. So that's all of these ordered pairs. And I'm going to try to draw a line nice and close right up to that boundary line there. So there is your solutions. In any ordered pair that I select, such as this one here at negative 6, positive 4, would produce a true statement when I plug it into my inequality. All right, let's try next example. This is not written in slope-intercept form. However, I can graph using my intercepts. So let's find my x-intercept by ignoring the y term. If I take 18 divided by negative 3, that gives me negative 6 on the x-axis. And if I find my y-intercept by ignoring my x term, I'll take 18 divided by 6, that gives me y is 3. All right, so here are my x-intercepts and my y-intercepts, and since my boundary line is just less than, I know that it has to be a dotted boundary line. So I'm going to create a dotted line through those 2 points. And I am going to test the point 0, 0 again to determine if this is in my solution. So if I put 0 in for x, I'll have negative 3 times 0 plus 6 times 0, and that will make the statement 0 is less than or equal, 0 is less than 18. And 0 is less than 18. So I know that my solution must lie in this half plane that contains 0, 0. So I'm going to shade all of that in as best I can. All right, and that's good enough for now. Let's take a look at one more example here. Now we have a word problem because it says you can spend at most $10 on grapes and apples for fruit salad. Grapes cost $2.50 per pound, apples cost $1 per pound. Write and graph an inequality that represents the amount of grapes, grapes, and apples that you can buy. That's a total math teacher move right there. All right, so we've got at most $10. And I know we're going to say X is our pounds of grapes. And we're going to say Y is our apples per pound, or sorry, apple pounds. So therefore, we have $2.50 times the number of pounds of apples, or sorry, grapes, plus $1 per pound of apples, and that all has to be less than or equal to $10 because we can spend at most $10. All right, so we're going to go ahead and graph this inequality. and then we'll do our shading in as well. Now in order to graph this, we're going to just get y by itself here, so we'll subtract over our 2.5x. That gives us 1y is less than or equal to negative 2.5x plus 10. All right, so our y-intercept is up here at 10, and it's got a slope of negative 2.5. So I'm going to come down 2.5 into the right 1, down another 2.5 into the right 1, and then we're going to repeat that pattern 2 more times here, and then finally right here. Okay, so there is our dots, and we can connect this with a solid line, but we're going to stay right here in quadrant 1 because this is the positive, right? And along the x-axis here, you got pounds of grapes, and then along the y-axis, you've got pounds of apples. All right, now one last thing that we need to do is to do our shading. And we're going to shade right inside this first quadrant because it only makes sense to have numbers in that combinations in that first quadrant, such as the combination of 1 pound of grape and 5 pounds of apples, or 2 pounds of grapes and 1 pound of apple. It doesn't make sense to have anything over here in the negative positive or the negative negative or the positive negative quadrant because you cannot buy negative pounds of grapes or apples.